Hello. So you're back with the promised video. This time we are going to implement the Monte Carlo integration in MATLAB. So yeah, first we'll do the coding while explaining, and then we'll make a short recap stepwise. So for that, to begin with, I have a curve with the discrete values x and y. Let's see how it looks actually. Log x y and extend first one 100. Hmm. This is not very real. Let's change this to line. Yeah. So this is the curve we have, and we are interested to find the area that is lying under this curve. So for that, now that we have defined the curve already, I have already defined the curve, but in your case you can have your problem curve at hand. So now, after doing this, the first step we go for is defining the bounding box. The bounding box is something that is going to enclose the curve very well, such that the curve completely lies within this box. Of course, its boundary are going to be uh, decided by the minimum and maximum values of x and y of this curve. So let's define the minimum and maximum values first. Uh, Defining the bounding box. So let's name it x min p. This is basically permeate x min p. Uh, this is equal to minimum of x 10. Similarly, x max p is equal to max of x 10. Then we go for y value. Y min p. This will be equal to min of y 10, and yeah, now again y max p is going to be equal to max of y 10. So we have defined the bounding box now. The next step is something called Monte Carlo sampling, or generating the uh, random points with the first step in that Monte Carlo sampling. First we will generate some random points just to fill this box. This is basically a box with extreme values along horizontal being x min and x max, and along vertical direction being y min and y max. So there's going to be defining a box, and in that box we are going to throw random points such that the number of points are going to more or less completely fill the box. For that we have to first decide how many points we are going to make. Let's say we'll take some 10,000 points. 10,000 points for now. Now what we do is we generate random points by using a random function in MATLAB. Let's call it x rand 10. This is going to be x minimum plus. So these random values are to be generated between x minimum and x maximum, and for that we write it this way: x min p plus. So this ensures that whatever the points are generated are to the right of the x minimum, which is the leftmost point, ensuring these are going to fall on the right of the left side of the box. X minimum p plus uh, x max p minus x minimum p. This is the interval. This is the interval times now we generate random of n comma 1. This is n rows and 1 column. So this essentially ensures that whatever the random points we generate are going to fall under the within the box. Ensures that the random points generated fall inside the bounding box. Yeah. Now similarly we generate y also. For y, again we name it y random plus y minimum plus y again y. So now our random points are generated for x and random points are generated for y. But yes, as of now we see that these x and y don't have any relation to each other. We'll sort that out in a while. We will automatically get sorted as we see later. Yeah. And how do we do that? How do we sort it out? We uh, yeah, we interpolate the main curve that we have at the generated random x values to be able to compare later if the random y values lie above or under the curve. Again, we interpolate the main curve at the generated random x values because we have random x values, but we should be able to know the y value of the main curve at the random x values. So that is the whole point here. For that, what we do is we interpolate this curve, interpolate the curve values at random x positions. This is the next step. Interpolate the curve values at random x positions. So yeah, now we name it, let's say y curve p, which is already there. Y curve p, no, it's not there. Y curve p10, okay. Y curve p10, we name it this. Y curve p10. This is going to be interpolation of the main curve only for the random points. So that means enter one of this is x temp and y temp, x temp comma y temp, and we interpolate it for x random temp. Interpolate the main curve for the random values of x to be able to find the values of that curve, the main curve, at the random x points we have generated. We can use spline I use other method too, but yeah, spline is more so for this test case we are using spline. Yeah, this interpolation is done. Now what we do is we count how many random points fall below the curve. Let's name that uh, count under. Let's name that variable as count under. Uh, count how many of the random points fall below the curve using the variable count under. Count under. Let's use this notation. This is going to be all the values. So basically it's going to be a sum of how many random values are under the curve. So 1 10 less curve 10. So this is going to be count under. So these are total number of points, the random total number of points that are under the curve. Next, we estimate the area of the box. Estimate the area of the box. That's the area of the box. Let's call it A box. A box equals base times height. So x min p. Yeah, so x max p minus, this is going to be the width base times the height y max p minus y min p. So this is going to be the area of the box. The next step is we have to calculate uh, how many of the random generated points are falling under the curve. That fraction we have to calculate. That is the variable we already have, count under divided by total number of random points. So let's call it area fraction. Area fraction. Okay. Let's call it area fraction yield equals this is total number of points. Total number of, so how many points are under the curve divided by total number of points. So how did we, this is simply n, right? Yeah, simply n. So this is area fraction. So let area under the box. Next is area under the box. We can call it a yield estimated. That is yield estimated because area under the box is essentially how much water we are getting. Yield water, pure water, let's say. Since the output is fluctuating, so area under the box is going to give how much water we are getting. So let's call it a yield estimate. A yield estimate equals this fraction times what fraction, area fraction times this a box. Okay, now we have area yield estimated also. Next, first let's see if this is having any errors. Then we proceed. No errors as of now. Okay. So now next step is we can display total area under the bounding box and estimated area uh, under the yield curve and those things. But yeah, we can do that now itself. Yeah. Now total area of the bounding box. This is one thing to be displayed. Next thing to be displayed is estimated area under the yield curve. The area we have calculated under the yield curve by this method. That is a yield estimate we have calculated here. This is one. The next thing to be shown is percentage of area under the yield curve estimated. Percentage of area. Okay, we can all let's leave it. Let's leave it. It's not that important. Next, now we go for visualizing this thing. Let's start visualizing this thing, and for that we consider new figure, and under the new figure, first we plot the x and y values. First we plot the x and y values, which were x temp and y temp. So plot x temp and y temp. Uh, let's put it simply. Since it is pure water, let's call it blue. Let's call it blue. And maybe line width. Let's keep it at 1. Okay, let's keep it at 1. Let's see if this is working. Yeah, this is working. Now, now we start plotting the random points one by one. Initially, if you just plot it, no, the MATLAB will plot all the random points at once. So instead of that, we plot one random point at a time, but very fast. So for that, we use a loop. We use a loop that is running for I equals 1 to this, yeah, length of this vector uh, for this range. We plot x and y random values. Plot x random of I comma y random I, and let's plot it using star, and yeah, star we plot it using star, and let's plot it in maybe a red color. Okay, let's plot it using red color. So this we need actually one point to be plotted at a time, at an instant. For that we have to pause. We have to induce a pause factor. Let the pause factor be 1 by n. 1 by n you can take. Very small. For this pause factor, we have plotted these things. Now let's see. Oh yeah, if this random points are covering up the box, then we may not be able to see the actual curve. It may hide under the box. We will plot this again. We'll hold on, and we'll plot this. We'll hold on here also. Yeah, now let's see what we get to see. Okay, yeah, this is how it is filling up. It's taking too much of time, right? So we can do one thing. We can plot a fraction of the points. Uh, we can plot, let's say, how many points are there, and this total random divided by, let's say, 500. 500th part of this we can plot, and then we can just go for plotting again all the random points at once. Just the animation we did, and we plot again these things. Now, oh, that was too fast. Let's take 100 or 50 maybe. Maybe 10. Yeah, now it makes sense. It's very sparsely covered. As you see, we need more and more points to fill. We'll cover up that also now. So we'll increase the n value to maybe 5e5. We'll increase the n value to 5e5, and let's plot only 800th part of this. So now I hope this will cover up well. Yeah, it does. This was the animation, and now let's go for checking what was the actual area. This is filled. Now, the total area of the bounding box is this thing. Estimated area under the curve is this. This estimated area under the curve is what the output of the system. This is what we need. So this is how we find the area under the curve using the Monte Carlo integration technique. It is simple, but yeah, especially if we have uh, very spiky curve, hmm, then it becomes crucial. Sometimes the integration technique, the numerical integration technique, maybe the trapezoidal or Simpson's one third or 3/8 or Weddell's rule or Bohr's rule, whatever it is. Sometimes they may fail because if the curve is very much spiky, we we may not be able to have a step size that can adapt to all the changes in the curve. The changes in the curve may not be able to be captured well. So for that reason, we use this technique. And once again, we end it with the animation again. Here we go. Yeah. And the area under the curve is this. So that's it for this video. Thank you.